So hello everyone, welcome. Today we have Anjay from ARM and Frank from Huawei, who are going to be talking about SME, the metrics extensions in ARM, and how to model them in MLIR. So Anjay, you can
Yeah,
go ahead.
let me. Can you see this?
Yeah.
Yes or no?
Yes.
Okay, cool. Right, so for those of you who don't know me, my name is Andrzej. I am a compiler engineer from ARM. I'm embedded within a larger compiler team that's responsible for enablement of scalable vector extension and scalable matrix extension. And by implement, I mean making it work to begin with, and then making sure it works well. And that's in LLVM-based toolchains. And I am responsible for SME support in MLIR. And the idea is to discuss today what's the best way to target SME from MLIR, basically. But I was also thinking, what is bringing us today is perhaps a bit larger question, and I just wanted to put it here at the top, is what is the best way to target CPU accelerators like SME from MLIR? Because from our perspective, SME is really an accelerator. It's different enough to regular CPU, and also the fact that we are struggling to find the right way, or the fact that we're having this discussion is also, I think, a sign that perhaps the path hasn't been really identified yet, and perhaps today is a good time to raise this question. But I will start by introducing SME. SME is a scalable matrix extension, so I will give you a brief overview of the architecture, mostly from codegen perspective. Do feel free to interrupt me if you have any questions. I'll try not to dive too deep, but if there's something that I'm missing, then just please let me know, and I'm happy to expand. Also, I prepared these slides for you as a reference if you're interested in joining the discussions and you're struggling to find some materials. So hopefully the slides will help you grasp the quirks of this architecture. I should mention that I tried my best to make these slides as accurate as possible, but ultimately it's the specs that are the source of the truth. So please always check with the specs. And also a lot of people help with these slides, with the content for the slides themselves. So massive thank you to everyone who helped me reviewing the slides or just helping build the understanding that has led to where we are today with SME. So I wanted to start by taking a step back and taking a slightly bigger picture, because SME itself is not really a revolution, it's an evolution. And I think that's important to bear in mind. So a lot of people are familiar with SVE, Scalable Vector Extension, that ARM introduced quite a few years ago. But I feel like fewer people are aware that after that, there was SVE2, which added a bunch of very useful instructions that make scalable vectors even more appealing. And fundamentally, SVE2 doesn't really introduce any like big changes, because that came with SVE, with scalable vectors. But it does introduce a lot of interesting instructions that make it more appealing to wider set of applications. And SME includes SVE2. So that's important, and I want to highlight that, because in order to have good support for SME, I believe we need good support for scalable vectors to begin with. And this brings me to, I think it's worth introducing scalable vectors, because I think it's still it might be still exotic to some people. It's not really, it's something that we have been using at ARM a lot, but it's not really so widely used. So I just wanted to quickly reintroduce in case you're not that familiar. So I think the best way to look at it is compare with neon registers. neon vectors. In the case of neon, you just have 128-bit wide registers or vector registers. And in the case of SVE, you are guaranteed to have 128 bits times v-scale. And v-scale is this multiplication factor that can be either 1, 2, 4, 8, or 16. And that means that you have at least one of those blocks of 128 bits, but you can have multiple of those. And here you can see an example of 512 bits wide vectors, for which v-scale is basically 4. And you don't know the value of v-scale at compile time, but that's totally fine because the ISA is designed in a way that you don't need this knowledge. Everything falls nicely into place. And one big element of that is predication and predicate registers. So there are 32-bit scalable vector registers, and there are 16 scalable predicate registers. And in those predicate registers, you basically have 1 bit per byte in a scalable vector. So you only need one bit to mask out a byte. And the example on this slide, I am looking at one scalable vector, well, one 128-bit wide chunk, and I'm looking at accessing just words. Word is a 32-bit element, which contains 4 bytes. So in 4 bytes, I have 4 masking bits, but I only need 1 to mask it out or not. So the remaining ones are ignored in this case. And that applies to other element sizes as well. And that's pretty much it. Now, I mentioned that you don't really have access to this scaling factor at compile time. And this can be a bit scary if you haven't worked really with scalable vectors. But scalable vectors are really well supported and established within LLVM and actually MLIR as well. So at the top, you have an example from LLVM where I use scalable vectors, and the only difference between scalable and fixed width vectors is this v-scale scaling factor, which you don't know at compile time, and it simply means I have multiple of those vectors of 8 or 4 elements. In MLIR, we have a bit more concise syntax. We just use square brackets to denote scalability. Now, you don't know what the value of v-scale is at compile time, and this can be a bit counterintuitive. But you have access to this LLVM v-scale intrinsic or vector v-scale up in the vector dialect in MLIR that gives you a SSA value that represents the scaling factor, and that's all you need. Everything else just works as if you had access to that value. So that's really the main difference. Now, SME is the key difference. The key thing about SME is that, well, because it extends SVE2, so it has those scalable registers, 32 of them, 16 predicate register. So that's similar to regular SVE, but on top of that, you get this 2DZA accumulator, which is used for matrix operations, and that's the major difference and the major addition. This ZA accumulator, and we call it accumulator because that's how it's used in most cases. You will access this accumulator through so-called virtual tiles. And the number of these virtual tiles and their sizes depend on the underlying element size. So it'll be different for I8, I16, I32, I64, I28. On this slide, I highlighted the case for 32-bit wide elements, for which you have 4 different tiles, and every tile is 4 times v-scale by 4 times v-scale. And this is important because at the final column, you can see the size of a Z register, and you can see it matches the dimensions, or at least, well, the number of columns or number of vectors respectively. And this is very nice. And this is what I'm trying to show on the picture on the right-hand side. It means that every column or every vector size-wise matches a scalable vector. And this is, I think, one of the key and one of the nicest parts of the design, that this, the fact that it's all so consistent. And also, as you can see, in the case of 32-bit elements, you have 4 tiles. In this case, the implementation I'm trying to depict is with vectors which are 512 bits wide, for which you'll have tiles which are 16 elements by 16 elements, because 512 divided by 32 gives you 16 elements. And the tiles are called ZA 0 to 3 because there's 4 of them, .s because I'm accessing single word elements, so 32-bit elements in this ISA. Now you can, so this is me trying to explain what these tiles actually are and where they come from. And this can be a bit counterintuitive. So I think this definitely helped me a lot to understand what is happening. The diagram is taken from this spec. So you can go to this spec yourself and check the diagram. I annotated the diagram to show you where these tiles are actually located, because intuitively you might, or at least that was the case for me, you might think that each tile is like a one of the corners, like upper left, upper low of the ZA array, but that's not quite the case. A tile is like a view into your ZA array. So the square thing towards the right is a ZA array. In this case, it's 256 by 256 bits. And I highlighted 8 rows. And those 8 rows is my ZA0S tile. It's 8 of them because it's 256. There's 8 32-bit elements in 256 bits. So hence 8. So yeah, these tiles are basically views into ZA, and you can have a lot of different views. This is the one case, but there's the architecture, or the ISA actually allows you to view them, and you can actually see on the diagram annotations on the left and on the right. Now, the spec doesn't really tell you, well, it gives a lot of the allows you to define your own implementation and leaves a lot of things to be defined by the implementation. So, for example, you can have one SME unit per CPU, or you can have one SME unit shared between multiple CPUs. It's really for implementations to define. I also separated the SVE file register on this slide. So SME could have its own SVE register file, and probably will do in a lot of the implementations, but I think that's, as far as I understand, this is also optional, or implementations can choose to share the SVE register file. But because you can have 2 SVE register files, you also need this concept of streaming mode, and also, so when you want to execute SVE instructions on a SME unit, you have to enter the streaming mode, and that's introduced to differentiate from non-streaming SVE, which you can consider as this regular SVE, right? So the SVE that we've had for quite a few years now, that's non-streaming SVE, the regular SVE, and the stuff that runs on SME would be streaming SVE. And this is important because you, or compiler, has to disable this streaming mode. And for that, we have assembly instructions, smstart, smstop. And these instructions are also used to disable the ZA array storage. So that's the extra complexity that the compiler or toolchain needs to take care of. And on this slide at the bottom, I'm showing you LLVM IR intrinsics for enabling, disabling ZA, and how that's lowered to assembly instructions. So you can try it yourself. So that's how it looks at the lower levels. And also in this case, I'm I'm enabling ZA and disabling ZA storage. So it's SM start ZA and SM stop ZA. But there's more of those intrinsics. So I already hinted that there's SVE and streaming SVE, and the notation that's used is SVE versus SSVE. And this is really important. It's important to distinguish between the two, because in the case of SVE, we have VL, which is vector length. In the case of streaming SVE, we have SVL, streaming vector length. And these can be different, and probably in practice, in most cases, will be different. You could, for example, imagine a regular SVE vector being 128 bits wide, and those streaming SVE vectors being 512 bits. But you could also have 128 and 128, which wouldn't be very exciting. Another thing is, I mentioned that SME includes SVE2, but there are certain exclusions which you need to bear in mind. One most notable example is our gather loads and scatter stores, and also neon instructions. And this is mostly to simplify the implementation, but there's an option for implementers to decide, no, we actually want all of that, and to have that enabled as well. So that's optional, but it's something to bear in mind, because it means that, when you generate code for streaming SVE, you suddenly have to restrict the kind of instructions you can use. Specifically, like you cannot use gather loads, scatter stores, unless you have an implementation that supports them. Few other notes about streaming versus non-streaming mode. ZA array and Z registers are cleared when you change the mode of execution. You can have nested SME kernels. So a SME or streaming mode kernel can call another streaming mode kernel. But suddenly things become complex because you have quite a few combinations. A streaming mode kernel can be calling another kernel that's not streaming mode, or can be calling another kernel that wants to have access to the whole ZA array. So there are some ABI considerations. And there's a bunch of LLVM intrinsics that model this and allow you pretty much full control. These intrinsics are designed primarily to support ACLE implementation, and ACLE is ArmC language extension. And we can choose to support them in MLIR, but we don't have to. That's an option that's something that that's for us to decide, basically. Because this is driven by the needs of C, really, and we are in MLIR, so things are a bit different. Right. Now I want to go over a few most notable instructions, just to give you a flavor of what's available with SME. I'm not going to go into great detail, but you can always come back. So the main thing that comes with SME is the outer product instructions. There are quite a few variants of those, and they basically work by reading to vector registers from the register file, computing outer product, and saving the output to one of the virtual tiles in the ZA array. That's why we call it the accumulator, because it's accumulating into ZA. In this example, you can see there are also, this instruction is predicated. There's a predicate register per input vector register, which means that you effectively have 2D predication, although we're using only those vector predicates to achieve that. The other things worth noting, again, operating on 32-bit elements, so that's because .s, that stands for single word, and I'm allocating into zeroth tile, that's ZA0. That's something that is hard-coded in the instruction itself. So that's one type of instructions. The other type of instructions are these multi-vector instructions. So in this case, I am reading multiple vectors from register file. I'm doing addition, and I'm generating multiple outputs. And there are, again, quite a few variants of that, but this is, again, a very nice addition to the ISA. And in this case, I'm only reusing the register file, but there are other instructions that allow you to reuse the ZA array, which means that you are basically given access to even more vector registers. Yeah, because like I highlighted previously, like these virtual tiles, their sizes, dimensions match SV registers. So in principle, yes, you can treat them as registers as well. There is a limited number of instructions like this, but they do exist. And I think that's yet another very interesting example. Right, but this meeting should be mostly about MLIR. So I want to go back to MLIR and discuss a bit what's been happening so far and what we're trying to achieve. So on the right hand side, you can see the diagram that I think it was Alex who originally created this one, and most of you will be familiar with it. I highlighted the key dialects that we are looking at, most notably lineage and vector, and I highlighted those because what we're trying to achieve is to be able to lower from lineage via vector to SME, because these are basically these funnel dialects, and we believe that by enabling lineage to SME lowering, we will be enabling quite a lot of frameworks, and that's quite important for us. I also highlighted TOSA, which I think will come with as no surprise. But I also added VOSA, which is a new dialect that we are developing at ARM, which is a sibling of TOSA for computer vision. I'm hoping we will be making it available publicly soon-ish. Yes, but fundamentally, yes, we work on VOSA and TOSA dialects. These are very important for us. These are lower to lineage, so hence our interest in the lineage and vector dialects. Also, we want to use lineage and vector because there's a lot of amazing stuff available, vectorization, there's also tiling and other things, and we just would like to reuse as much as we can. I'm also highlighting a few assumptions on the left that we are making just now, and this is, I think some of these have already been mentioned by Frank on Discord, so probably no big surprises here. So for now, we're not really looking into nested kernels to avoid any complex ABI considerations. I did mention that, you know, there are those LVM IR intrinsics, and if we allowed nested kernels, then we suddenly have to worry about tracking and preserving, saving, loading the ZA array, and also making sure we enter and leave streaming mode accordingly. And we believe we can actually get quite far without supporting that. We won't support using mixed types when accessing ZA, because then your tile sizes, virtual tile sizes, will differ. And again, you have to keep track of, you know, not accessing overlapping tiles. And that's another complex problem that we'd rather just avoid for now. And this also means, well, this is linked to the final point. We will assume that every SME kernel will fully utilize the ZA array. And we can do that because we won't be calling kernels and we won't be sharing the ZA array. We'll just assume that every kernel has full ownership. Now, these are simplifications that we may want to relax later. But just to begin with, it feels like very sensible. Okay. So what does it take to support SME and MLIR? There's actually quite a few steps. I already hinted the streaming mode and the fact that, well, that we need to enter and leave that and enable and disable that A array. That's already done in MLIR, and that's achieved via function attributes, basically. So at the top, you can see I highlighted two attributes that have been added recently, ARM streaming and ARM ZA. And these are lowered. One of them is lowered to another attribute at the LVM dialect level. The other one is lowered to calls into intrinsics. So that's supported. We can already do that. We have a integration test running upstream as well. So that's already functioning. I won't go into detail why we lower one of them into another attribute and the other one into intrinsics. Unless you really want to know, then I'm more than happy to dive into details. But there are good reasons for that. Now, ultimately, what we would like to achieve is to get from LINAC matmul to SME, good SME code. And we would like to achieve that via vector dialect, because vector dialect has vector outer product operation and SME has vector outer product instruction. So that makes a lot of sense. And we already know that we can lower LINAC matmul to vector outer products. So there's already quite a few hints that this is a very interesting path to explore. One important constraint to keep in mind in the context of SME is the fact that in this particular case of 32-bit elements, we have access to 4 virtual tiles in SME. So we have access to 4 accumulators, which means we want to split our LINAC matmul in outer products accumulating to 4 different accumulators. And that's the example that I'm showing at the bottom. It's handwritten by myself and my colleagues at ARM. We just sat down and tried to, by hand, write what we think should be a good representation for SME. Obviously, I couldn't fit the whole code, so I only focus on tiling the output matrix, which is basically the accumulator. We tiled it into 4 different sections. And then for each section, we just have this outer product, or we would have 6 outer products because there are 6 columns/rows in the input matrices. So there'll be 6 of them accumulating to the corresponding tile of C or virtual tile at the SME level. But what's really key here is that, this is nothing SME specific. All I'm saying is I want my LINAC matmul to be lowered to outer products, and I want it to be lowered in a way that you will be accumulating to 4 different accumulators, and that's it. And you can see the full example on GitHub. I'll give you a link on the next slide. But what's really key is that you can generate that code already using MLIR, using this transform dialect sequence. And that means that we can already use vanilla MLIR and to lower LINAC matmul into something that would be very friendly towards lowering to SME. And you can find a full example on GitHub with annotations and comments that explain exactly what I have in mind. But yeah, the key message is there's nothing SME specific here so far. All I'm saying is split the matmul into 4 different outer products for 4 different accumulators, and this can be done, which is amazing. And this is one of the big reasons why we want to reuse what's available in LINAC and vector dialects and the infrastructure that surrounds it. I'm not going to go into more detail. If you're interested, then you can view the GitHub link, and if you have any questions, then you can also ping me. And I should say that I got a lot of help from quite a few people preparing this example, so thanks very much to everyone for that. So this is basically what we are aiming for. I also wanted to give you a list of, mostly for reference, links of what's been happening with respect to supporting SME and MLIR. There's quite a few things happening. Scalable vectorization is very important because SME is a scalable matrix extension, and we need to generate scalable vectors. And it also includes the SVE file register, so that's important. Streaming SVE enablement, that was the part with the streaming SVE attributes and testing is very important for us. So we made sure there's at least one bot with a QEMU, which supports SME and runs one integration test. So far, we're working on adding more. Yeah, and there's also, so Frank recently submitted a patch that adds LLVM IR intrinsics for SME. So that's also happening. And independently, there's a patch hopefully to be merged soon that lowers vector transfer right to the zero SME instruction, which just zeros the whole accumulator. I have one more slide, a bit of a digression, but I wanted to make sure that we also cover prior art because I started by asking this generic question, like what's the best way to support CPU accelerators from MLIR? Yes, and I think it's worth looking at other examples, AMX being the most notable one. That was added by Art a while ago, and you might be wondering why not reuse what's been done over there. So my answer to that is we are reusing that. It's been insanely helpful as a reference implementation, and we revisit that a lot. For example, setting up integration tests is very tricky, and I'm super happy that we can just use a existing example as well as for other things. But there are some notable differences between AMX and SME, and it's not immediately obvious that there's enough of an overlap. Also, one could be wondering, well, both are matrix extensions. Perhaps we could work on adding matrix type to MLIR, but then vector type is for ND vectors, which includes 2D vectors, which is a matrix. So there's no really need for that. So yeah, not sure. Like the other thing is that AMX support is implemented through this hardware vector dialect, and I believe that's the approach that Frank is taking. So Frank will present on that, and perhaps he will be able to tell us, what will be the advantages of that. But yeah, this is all I have for today. Sorry, I just completely blasted through it. Hope it wasn't too quick. So yeah, if you have any questions, then otherwise we can perhaps Frank can present what he has on the SME dialect and the approach that he's taking.
Yeah, I think it's a good time for questions. So please go ahead. I can start. I don't know if Art is here, but I can provide a bit of context on the AMX dialect. This dialect was introduced mostly for experimentation. So if you look at it, there is no high level dialect that can lower to it. So you cannot go to AMX from Affine or from Linux right now. It was more like for experimentation. So we have it as more like an entry point to some extent for testing. And also the constraints are different. That's one of the questions that I have. In AMX, you need to have like a very specific layout. You have to reshuffle the data. Is it something that is required in SME to some extent?
No, not really.
Okay, great.
It's just grab a vector or yeah, loading into ZA perhaps will be a tiny bit fiddly, but ultimately these are just vector load instructions. There's nothing. I've not seen anything worrying in that area. Or complex. I took a look at AMX, and yeah, I think in that respect, AMX is quite challenging compared to what we have to deal with for SME.
Okay. So what? I think there might be some like very small challenges in the when it comes to the widening instructions. right? Because I think the wedding outer product instructions require the input vectors to be more of a small matrix, right? And in practice, I think without the gather instructions, which are illegal, it might be a little bit challenging to format those into the correct kind of layout that's required. But again, for the time being, I think we can. Yeah, I think the interest right now is mostly floating point and double precision, and we can probably gloss over that for the time being.
Okay, great. Yeah. Any other questions?
So as you mentioned, the conversion happens with the assumption that matmul is present in linalg and it starts down from there. Is there a plan to support more ops via this path down to SME?
Yeah. Next on the list are convolutions.
Okay, and I mean, do you expect to reuse the same sort of like dialects, set of dialects for this work as well? Or do you expect like more different kind of transforms to be applied beforehand? It can be lower.
So we are focusing for now on lineage, TOSA, and VOSA. And we are looking, I'm looking specifically at VOSA and what we can do for VOSA specifically and for computer vision. So we're not, I'm not going to venture beyond those dialects in the near term, but our ambition obviously is to support or make SME available to as many frameworks as possible, but you have to start somewhere and prioritize. So I guess my question would be, can you see another dialect that we should be paying attention to?
Like I'm quite new to like ED and MLIR. The reason for asking that question was are the different kinds of ops that we see commonly in ML networks, are those going to be lowered without the help of VOSA and TOSA as well? But as you mentioned, like VOSA and TOSA are the priority for even for this part. So in the future, will there be a path without VOSA and TOSA?
Well, yeah, absolutely. I mean, the reason we're looking at lineage, well, we need support in lineage to support VOSA and TOSA. So we want to support as much in lineage as we can. We are driven by VOSA and TOSA needs because that's connected to specific products or technologies developed within ARM, and it just makes much easier to motivate. So, but if you're asking about things beyond these three dialects specifically, then not really. I don't have anything specific in mind. But the reason we're looking at lineage is to make it generic. Ultimately, SME is a outer product engine, and we want lower outer products onto SME, and that's the goal. It's not really VOSA, TOSA, or lineage per se that are the goals. The goal is to lower as much code, as much outer products onto SME as possible, and we just identify these dialects as very good starting points.
Okay. Yeah, thanks. Makes sense.
Okay, I think we should move to the next presentation. I want to make sure that Frank has enough time, so then we can take more questions at the end. So,
okay, thank you, everyone.
Frank, please go ahead.
Yep. Yeah. Let's see. All right. I assume you can see my screen right now. So yeah. So I kind of just want to preface by what what we want to achieve with the SME dialect. And in particular, we want to kind of focus on the outer product instructions, which are basically I think the core to the whole SME ISA, I guess. So yeah. First of all, we want to kind of address some of the challenges in bridging the gap between the tensor or slash vectors with the SME data tiles. I agree with Andres in the sense that we want to reuse as much as we can from the vector dialect and that kind of thing, but also we want to keep some of the flexibility that we have with the outer product instructions that SME provides, in particular the predication, right? We want to kind of keep the ability to predicate some of the input vectors. So I think this presentation is not really, I mean, it's more of a discussion topic, kind of raising some questions rather than just presenting the dialect as it is, because that's still very much a work in progress. So LLVM's representation of the data tiles, especially for the outer product instructions, are a immediate integer, right? So in that sense, it's kind of difficult to translate directly from SSA vector values to these instructions. So, since we need some sort of register allocation, and there might be a question, maybe this is better suited to do in LLVM, but And secondly, as I've mentioned, the outer product instruction has predication in 2 dimensions, right? One for each vector. And currently, as it stands, the vector mask can only handle 1 masking vector. And there's, and I think Andres also kind of touched on this, where he translated from lineage to vector outer product directly. But so at that level, I feel like we might be losing some level of flexibility from what's provided by the actual hardware. So this is kind of my initial idea for what might go inside of SME dialect, and I think the core really is just the outer product instructions, and everything else is pretty much just the allocation of the tile that I talked about. And potentially, if we want to go with this approach, then we might also want to do some instructions to do the filling and reloads of these tiles as well. Okay, so this is kind of the set of instructions that I had in mind for kind of allocating a tile. So we would basically keep a list of tiles that we have allocated, and according to the ISA, there are certain tiles that we could kind of have at the same time. For example, we could have a F64 tile, which is a double word tile, and a F32 tile at the same time, as long as they are for different, they're occupying the different rows, I guess, in the actual data accumulator. And I think the consensus is that we kind of want to use a vector as the actual implementation for or representation of this tile, but also there might be advantages to using an opaque construct as well. However, that would also make it harder to interface with other vector ops to use this data tile as a as a collection of vectors. And secondly, there's the use of these tiles. There's the outer product where it was the masks, and and additionally, we might want to deallocate the tile with a store op, but again, this is still kind of optional and debatable. Also, what do we want to do if we want if there was a read after write, right? So in this case, the tile 0 has been accumulated into right, with this outer product up. And if you want to read this again, then either you have to make a copy of this before you do this outer product instruction, or we just emit an error, right? Yeah. Yeah, I think I touched this already. So yeah, I guess, yeah, this is really just a very high-level overview of what I kind of want to achieve with a SME dialect. Generally, it's, I guess, what it boils down to is a trade-off in flexibility and generality, I guess. And yeah, allocation ops makes the tile management easier, but I guess it's not actually strictly necessary, as long as whatever is generating these operations know how many tiles are available and the restrictions there are. And yeah, it's debatable whether or not we want to do this sort of pseudo register allocation in MLIR. And yeah, and another key point is the representation of the tile itself, right? I think in general, it's probably a good idea to keep these tiles as a vector type. So yeah, this is really short, and yeah. Are there any questions?
Thanks, Frank.
Go ahead, Andre, you first.
So you mentioned yeah, thanks for the presentation. I mean, a lot of it makes sense, but like, for example, how do you see getting from here to lowering Linalc Matmul, for example? Because yeah.
There might, yes, this is the part where it's a little bit ugly, right? We would probably need to have a list of ops that we want to support in the launch that we want to lower to this our product instructions, right? And yeah, again, this might be a little bit ugly.
For your question about or your points about tile allocation, I'm avoiding the term register allocation, and I'm trying hard to switch to tile allocation instead, because there's only one register and we are dealing with virtual tiles.
Right.
And that leads to a lot of confusion, because when you mention register allocation, that's a very complex problem,
right.
And I think that scares a lot of people, including me. That's why I'm like also trying myself to convince it's a much easier problem. You did mention, you raised a question, perhaps it's a problem to be solved in the backend. So at least from our perspective, from ARM's perspective, I can tell you that that's not going to happen in timescales that are in timescales that matter to us in terms of supporting SME from MLIR, not because there's no will, but it's also not clear whether that's actually necessary. And also it's going to be a super challenging problem, because in the case of these tiles, it's different to register allocation. With register allocation, you usually have a fixed number of registers. Here, you have a varying number of virtual tiles depending on your underlying element size. And it becomes even more complex when you mix different element types. So that's one reason. And the other reason is that you can have vertical and horizontal accesses to the ZA array. And then the overlapping views complicate the problem even more. So I know that that's one of the reasons. These are the reasons there's very little appetite at the moment to try to challenge that from the LLVM perspective. It might happen, or perhaps somebody will volunteer to do it at some point, but it's not happening today. And I don't think we can expect that to happen in the near future, at least not as far as ARM is concerned right now.
So how do you handle this? I guess the user can write intrinsics, right? How do you handle this in that situation? Does the user have to deal with all the virtual register allocation thing?
Yeah, that's basically, if you are writing code in C and using ACLE, the intrinsics force you as a user to track the tiles that you're using, and you are effectively, as a user, doing this tile allocation and you're solving this problem. So because it's basically a attribute that you pass to the intrinsic, it's an intermediate, and that's the design we have today. And again, there are no plans to change that design. But the other thing that Frank also touched on, and it is a big challenge and concerning, is yes, ultimately we can only use so many tiles. Like, we know we have 4 tiles, and we cannot generate code that would lead to more tiles. But the point I was trying to make is that, you know, we can at some higher levels of abstraction decide, okay, lower all linear math modes to SME, and by the way, you can only use 4 allocators. And once we specify that, you know, and we go through linear math mode lowering, all the knowledge that we need is like 4 accumulators. There's nothing specific to SME in there. You're not leaking any architectural knowledge. It's just like, use 4 accumulators, please. And I hope and strongly believe we can do that for many other things. But with this approach, I am limiting myself to linear mathmal and few other ops of most interest from my perspective. I think with Frank's approach, you'll be able to lower pretty much everything at any time. So it's much more generic. But then there's also a question like, is SME going to be used for all these generic things? And my answer to that today is, I suspect we will mostly use it for really hot kernels like matmos and convolutions.
Yeah, I think that I can perhaps provide some feedback or some history here. I've been reviewing some of these proposals about targeted specific dialects, and usually what happened there many times is that, you know, we open a dialect, we just throw a lot of operations to it, and we kind of create a silo. It's very easy just to, you know, fork from the main MLIR representation and just go into your dialect and do whatever you want. And sometimes a lot of things are reusable. And what usually happens is that people just go and leave those operations there or move to work on something else. And we have quite a few technical depth in that sense. So that's why I've been asking in these proposals, what do we want to do? What is the plan? What kind of transformations are we planning to do? Because if it's just like, you know, a one-to-one lowering from a vector dialect operation to an LLVM intrinsic, we are now MLIR is now in a state where we can mix LLVM intrinsics with the rest of the core dialects. That's something that was not the case like a few years ago. That's why some of these dialects were introduced, right? So I think that's kind of the thinking. I have the impression that we still don't know what we really want to do, and perhaps going directly from the vector dialect to intrinsics without using a dialect will give us some time to really understand what we need and design the SME dialect in a more proper way. That's been kind of my thinking in general.
Right. So there's a few things that we while we are working out internally that you know, utilizes SME in more ways than just, you know, a matmul and that kind of thing. But I don't think I'm allowed to talk about them here, so I might just leave it at that.
I mean, we can definitely take into account, you know, more complex cases and see how we can model them. And again, I don't see a major problem with an SME dialect. It's more about understanding why it's needed and what kind of transformations we want to do there.
I mean, if we can't see how it's used in practice, it's kind of difficult to work with you on it.
Right.
I mean, I feel like we're coming at it more from the approach that Diego's mentioning there. So I've been looking at like how to go from something really simple like linalg filter to zero, to the zero instruction, and ironing out problems there. Which I've not got some, design or anything about, what a dialect would look like for this, but it's just trying to go from vector to intrinsics and seeing if it can even work, what the issues are, that kind of thing. But it's very practical. It's helping us find issues like how to enable streaming mode, how to turn the ZA on, these kinds of things, and writing integration tests that show, something is happening end to end. So I feel like that's what's maybe missing from, this proposal to have higher level custom ops in the SME dialect. And it'd be useful if you could share that.
I will just quickly add that, the things that you're showing here, I feel that we will need them at some point. Today, I don't see the need for at least what we are trying to achieve. And I feel perhaps it's too early, at least from my perspective, because I don't see needing this today, yet we are succeeding in generating and running some SME code from MLIR, if that makes sense. I appreciate you might have cases downstream or internally where you do need it, but it's hard to see that today based on this proposal.
I see.
So, sorry, a question. So, if I understood correctly, the idea is to when you provide this more flexibility with the SME dialect, is to have special cases of operation, how you lower them to this dialect. Why not use like kernel or microkernel written with using the intrinsics for that? If it's only a limited number of things that you want to lower to very specific SME, it seems like you want a lot of control.
That is a good point. Right now, we are preferring to interface directly with. Yeah, that is a approach that we haven't quite thought about before. So, yeah, thank you for the suggestion.
Okay, I think we're running out of time, so maybe we can continue the discussion on Discord or Discourse, and if needed, we can have another meeting. We can talk to Mehdi about that. So thank you very much to the presenters and everybody for attending. It was a great discussion.
Thanks for hosting and for organizing, and everyone for participating. Thank you.
Yeah, thanks for the presenters.
Yeah, cheers.
Cheers.